15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
It's one small step for man, one giant leap for mankind. Oh, that looks beautiful from here, Neil. It has a stark beauty all its own. It's like much of the high desert of the United States. It's different, but it's very pretty out here.
Hello once again, and thank you for joining us on the podcast known as Space Nuts, a special edition. We're dedicating the whole program today to Apollo 11. As this podcast leaks out over the ether or the internet or wherever the heck it goes, we will be looking back 50 years to the day when mankind kicked the moon. And as a part of that, we'll be looking at not only that particular event, but also some of the things that have come out of the Apollo missions. And joining me as always is one Professor Fred Watson, astronomer at large. Hello, Fred.
Hey, Andrew. How are you doing?
I am very well.
That's
well.
Good.
Good to have your company on this special occasion. And something I've been looking forward to. I know we've been sort of building up to this for quite some time, and I've seen so many news reports and specials popping up on television and in newspapers and on social media, and all the conspiracy theorists are out in force at the moment, but we're not going to go there. But I thought I'd start off with an amusing anecdote. I was watching a report yesterday on an Australian news network where they were looking at the anniversary of the moon landing and the first step on the lunar surface. And the reporter said it was the first time mankind had set foot on another planet.
There you go. That's a promotion for the moon, is that?
Yeah, sure is. Big promotion. Huge promotion. We must be orbiting it, is what I gleaned from that remark. But
maybe so.
It just sort of indicates perhaps a little bit of ignorance or maybe a bit of misdirected creative license, but it is certainly not a planet. And a few of us were talking about it at the radio station today, Fred, and one of the things that came up was the fact that since that moon landing, 2 generations of human beings have been born. And I thought, yeah, well, that makes sense. I've had children since then, and now one of those children has children. So yeah, there'd be 2, maybe 3 generations in existence now that weren't around when the moon landing happened, which is something to ponder. 50 years doesn't seem like a long time, but a lot can happen over that kind of time frame. Anyway, we are going to look at the mission itself as a sort of a precursor to a couple of other things. We want to focus on the legacy of the Apollo missions. One of the big, I suppose, arguments that seems to center around astronomy and space travel is what's in it for us, as in humankind. And, well, the Apollo missions probably are a way of really defining what's in it for humanity. So that's what we're going to look at today. We're going to focus on what came out of it scientifically, what came out of it technologically, and there are a few what Fred has referred to as intangibles that might surprise you. We'll get to them a little later. But the mission itself, Fred, one of the things that's come up is, where were you? I was at home. I got sent home from school because I was a naughty boy. No, everybody got sent home to watch it on TV. Of course, in Australia, we saw it on the calendar the day after, I think it was. Or something to that effect, but it was about 1 o'clock in the afternoon, our time.
You're referring to the moonwalk rather than the
moonwalk, yeah.
Yeah.
So
yes, you saw it in the afternoon on the Sunday.
Yeah. Was it a Sunday?
Well, it was. Sorry, I beg your pardon. It's Sunday this year.
It was a school day, as I recall, when I saw it in 1969, and so we were all in the lounge room, crowded around our tiny little black and white television, taking it all in. I'll never forget that moment. I was 7 years old, and it was astonishing. Where were you?
I actually think it was a Monday.
It could have been.
Yeah, because I took the day off. So what happened? You see, I was in the UK And my job at that time was an optical physicist working for a company that built large astronomical telescopes. But in fact, the telescope I was working on was a small one. It had a mirror 10 inches or 25 centimeters in diameter, and it was going to fly on board a spacecraft called TD-1, which eventually was launched in 1972. So I was working on this space mission in this lab, but all of us in the lab were completely fascinated by Apollo. We just wanted to be the Apollo astronauts. We didn't want to be working on boring things like robotic ultraviolet cameras for spacecraft. So it was a very heady time. So the launch itself was covered on TV, but the landing and the moonwalk, as I remember, I think it was a Sunday afternoon actually that this is our time in the UK, that there was coverage of the landing, the touchdown on the moon, but then the BBC shut down everything because it was 12:30 in the morning. And, of course, in Britain you don't go beyond midnight, and so I had to watch.
Hilarious.
I had to watch a recording
of
the moonwalk the next morning. I got up, I think it was 6:30. I got up to watch it on TV, but it was a recording by then of the moonwalk. But yeah.
Well, as I understand it, Eastern Daylight Time in America, it was 10:56 p.m. when he stepped on the moon, which would have put it later in the day for the UK and the next day for us in Australia. We saw it on the Monday, but it was actually a Sunday, as I understand it. But yeah, there we are. And I'm sure a lot of people have been having this discussion about, where were you? It was an incredible achievement in terms of the fact that they got there, the test mission of Apollo 8 to go out there and do a lap of the moon and go, oh, well, that's as close as we'll ever get, and fly home. And I think at Cape Canaveral at NASA now, they still have the control room set up for the Apollo 8 mission, and you can sit through a replication of the launch, which is exciting. But it was Apollo 11 that captured the imagination of the world with the first step on the moon. And I feel privileged to have met Buzz Aldrin and talked to him about it some years ago. And, he was an amazing man. Neil Armstrong, of course, no longer with us. And Michael Collins is doing a lot of media as we speak in the lead up to this momentous anniversary. But, Fred, I think telling the story of the Apollo moon landing and the missions is only part of it, because the planning and the science and the technology that went into it wasn't only beneficial for the missions, it was beneficial for humanity, as we're going to discuss. So I suppose we can start off by focusing on the scientific legacy of the Apollo missions.
Indeed, which we still, it's still cutting edge science, is this. So what did the 6 Apollo landings, and you remember, so just very briefly, we're celebrating Apollo 11, but the sequence of Apollo landings culminated with Apollo 17, which landed in December 1971. Apollo 13, of course, didn't make it to the moon. They returned to Earth safely, but didn't land on the moon.
Which is really good, because we wouldn't have seen all those Tom Hanks movies if they didn't get back. So
apparently not.
Yeah.
So that's right. 12 people walked on the moon in those 3 years. The first time anybody had ever set foot on another world, not another planet. And of course, that Apollo 17 landing in December 1971, that was the last time humans went beyond low Earth orbit. We've done a lot in space since then with the space shuttle and the International Space Station, but we've never ventured as a species beyond low Earth orbit, apart from robotically. So we've done it, vicariously with our robotic spacecraft, but we haven't done it physically. So the science that came from it, the sum total, 382 kilograms of lunar rock and soil, something like 8,400 images taken on the lunar surface and many more from space as well. And all the scientific data that comes from, that sort of venture. The Apollo astronauts left seismometers behind to record moonquakes, which come from both the shrinkage of the lunar crust and from meteorite impacts. Those seismometers, I think, worked for about 7 years. I think they faded away sort of towards the end of the 1970s. The other one, though, is the laser reflectors, which were left on the moon's surface.
Yeah.
These are what are called corner cube reflectors. They're bits of optics that have the property that if you shine a beam of light into them, it comes out in exactly the same direction as it went in, or the reverse of that direction. So it means it doesn't matter what angle you set these things up at, and it doesn't matter sort of at what angle the beam comes in from Earth, because it's a laser beam coming from Earth that's used for this, it always goes back the same way as it came. And that lets us measure very accurately the distance to the moon, because you can time the flight of the laser beam. You make it a very short pulse. It takes about 1.3 seconds to get to the moon and about the same to get back. But you can measure that very accurately, in fact, to picoseconds, so that what you get is a measurement of the moon's distance to better than a centimetre, or 2/3 of an inch if you're working in inches. So remarkable accuracy, and it's because of that we know that the moon is receding from Earth at 3.82 centimetres per year. That's because of a process called tidal friction. The moon gains energy actually from the Earth's rotation, and it responds to that by moving away. As you give energy to something in orbit around something else, it moves away from the primary.
Yeah, my level of energy repulses my wife.
It had not escaped my attention. No, I'm sure that's not true, Andrew.
Now,
we'll get on
did
one day.
we know about that drift before the Apollo missions?
So that's a really good question. I think it was surmised, but and in fact, there are measurements you can make with optical telescopes, but I don't think it was anything like the kind of accuracy that we're talking about now. The other thing is that, as well as the moon moving away from us, this process of tidal friction slows down the rotation of the Earth. It actually slows down both bodies, but the moon is already slowed down, so it's already locked into facing us all the time. The Earth is well on its way to that process. In several tens of billions of years, one side of the Earth will always face the moon, but we're not there yet. So what happens is that the rotation of the Earth is slowing down slightly, and that's one of the reasons why every 2 or 3 years we put in a leap second into our calendar or our clocks, either on the 31st of December or the 30th of June. And that's to keep the atomic clocks of the world in sync with the rotation of the Earth, because of the fact that, we now have atomic clocks that can detect that slowdown of the Earth's rotation. We've got lasers that can detect the moon drifting away. So it's all very neat and tidy. But to deal with it, we've got to stick in these leap seconds.
Yes. One of the other things that's come out of the Apollo missions is learning of the relationship between the Earth and the Moon. I suppose we always wondered how it got there and why it is what it is, but we've now been able to collect samples and do some comparative work. But it also opened up a mystery as to why it is so.
Yes, that's right. So one of the popular theories in the early 20th century was that the moon came from the fact that early in its history, the Earth was spinning so rapidly that centrifugal force, dislodged material from its equator, which formed the moon. It doesn't work, doesn't that theory? Because we know from other arguments that the Earth never rotated fast enough for that to happen. It would have had to go around once every 2 hours for that to take place, and it apparently never went round faster than once every 4 hours. So it was whizzing round, but not fast enough for it to be just centrifugal force. So since the 1960s, we've assumed that what happened was that the Earth was hit by a Mars-sized object in the early history of the solar system. We're so confident of this, we give it a name. We call it Theia, or Tia. It's the mother of Selene in Greek mythology, mother of the moon. So this object hit the Earth probably within the first 100 million years, although that's been narrowed down a bit more recently. I'll explain in a minute. So what you've got is this huge cloud of debris, which surrounds the Earth in a ring, and in fact then condenses into a moon. Last week, there was some observations reported from the ALMA telescope, which is the Atacama Large Millimeter Array in northern Atacama, near San Pedro de Atacama in Chile. I was there last week. The ALMA has detected a cloud of material around a planet which is orbiting another star. And that is thought to be a moon in the process of formation. It's the first time we've seen it. But we believe that happened in the case of our own moon, with this material from Theia, the colliding object, coalescing into the present-day moon. The problem with that model is that there is something called the oxygen isotope ratio, which is a detail of chemical analysis. But it turns out that all bodies in the solar system have got different oxygen isotope ratios. But the moon and the Earth, and we know this from Apollo, have exactly the same. And what that suggests is that the moon actually came from material from the Earth, whereas the collision theory suggests that what you get is material from the colliding object rather than
which means that everything should be different.
Yes, because there's only a 1% chance that Theia would have the same chemical isotope composition as the Earth. So you've got a problem there, exactly as you mentioned. And a few people have tried, different scenarios. If you kind of fiddle the numbers a bit, you can make it work. But it was never very satisfactory because a collision happening at some random angle would always produce material that were made of the colliding object rather than the collidee, the Earth itself. Until 2 months ago, because in April this year, and you and I spoke about this on Space Nuts, but scientists in Japan and the United States seem to have solved the problem because they've done something which should have been pretty obvious, but really none of us thought of it before. If the collision happened early enough in the Earth's history, say within the first 50 million years, then the Earth was probably was still covered by a magma ocean. It was a liquid rock surface. It was so hot, you had this liquid ocean of material. And if you then take something solid, and Theia was assumed to be solid, it's much cooler and much smaller, so it would have cooled much more rapidly and solidified more rapidly after its formation. That bangs into the Earth with its slushy outer layers. And what you get in that circumstance is the material that formed the moon is actually made of Earth-like material, and it works really well. It seems like a big step in our understanding of where the moon came from.
So technically speaking, we are living on two planets.
In a sense, that is true because one came from the other. It looks like in the models that these scientists have made, the material that was Theia gets sort of plummeted out of the Earth-Moon system, and it's still a stream of debris, but it's not captured by the Earth. It's actually going faster than the Earth's escape velocity. So so we're a double planet. Just going back to your comment right at the beginning that somebody said it's the first time we stepped on another planet. People have argued that the Earth and Moon should be regarded as a double planet rather than a planet and its satellite. And the argument is that the moon's orbit is always concave to the sun. I don't know whether you realize that, but no. as the Earth goes around the sun, it takes the moon with it. And so the moon's orbit is always concave. It's always, never is it convex to the sun. It's always concave to the sun. However, most people rubbish that argument because the real test or the litmus for a double planet is if the barycenter, the center of mass of the two, is actually outside both bodies. And that's the case in Pluto and its moon Charon. Now, Pluto, of course, is a dwarf planet, but Pluto and Charon really are a pair of dwarf planets rather than rather than a dwarf planet and its satellite, because the barycenter, the center of gravity, is outside the body of Pluto.
Okay.
In the case of the Earth and Moon, the barycenter is inside the body of the Earth. So we are definitely a planet and its satellite.
Very good. All right. We've got a lot to get through, so we will move on. But it's been fascinating so far, talking about the Apollo missions and the Moon and the legacy of those Apollo missions. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we have spoken about the scientific legacy of the Apollo program. What about the technology? Now, I don't know if this is true or not, but I heard a little piece of information some years ago that suggested we would not have the microwave oven without Apollo. I'm not sure if that's true or if it's an urban myth, but
could be.
Could be true.
Well, yeah. So it is true that one of the things that Apollo pushed was the miniaturization of technology. I mean, it's a bit. It seems a bit curious that the biggest rocket ever launched,
the Saturn V.
The Saturn V should actually, should spur a miniaturization. But they did. They had to make everything smaller, and it may well be that the what are they called, the things that generate the microwaves? I've forgotten the name of it. That's ridiculous.
Microwave
Inside
ovens.
The device that does it. There's probably listeners there yelling out the name loudly at the moment, but I've forgotten what it's called. It's that device, which will come to me shortly, I'm sure, was almost certainly miniaturized. They started their life actually in radar, wartime radar, these emitters of microwaves. However, probably the most notable path of miniaturization that we think about with Apollo is with computers. Because at that time, during the 60s, computers were starting to become, readily available. They were being built commercially. IBM and ICL and companies like that were building these machines. When I went to uni in 1963, I did a course in computer science, and we had an IBM machine in the computer lab, which I think weighed several tons. It had its own electricity board to break the circuits, its circuit breaker board. So it probably consumed several kilowatts of power. And that was the best we had then. So that was at the beginning of the 60s. That probably dates from about 1960. By 1979, you've got the Apollo guidance computers, which were very much the things that were being used on board the spacecraft. There were two of them, one in the command module, and of course that stayed in lunar orbit, and one in the lunar lander, the LEM, the Lunar Excursion Module. So by then, these things had come down to a very lightweight 32 kilograms. What's that, 70 pounds or something like that? 2.2.
I can never remember that conversion.
Yeah, 2.2 pounds per kilogram.
Yeah,
so it's about 70 pounds. And they also consumed about 70 watts, which is the power taken up by a fairly bright light bulb of the old incandescent type.
Yes, that's right.
And that was state of the art. That was, the just what you needed for computing the orbital parameters. It was still pretty advanced stuff.
Back then.
Yeah, for back then. But of course, it was all in gobbledygook terminology. You had to type in coordinates, and there was nothing like a tracker pad or a mouse or anything like that. It was all about just typing numbers in and getting numbers out.
I suppose the equivalent to a DOS system.
Yeah, well, it's far cruder than DOS.
Yes, probably, yeah. I think that was well demonstrated in the movie Apollo 13, where they were trying to re-coordinate their position and achieve some sort of guidance, and they were doing all the mathematics by pencil and paper.
Yeah.
And had to then hand program the computers to alter course. And it was just,
that was right.
That's what it came down to. Were you thinking of a cavity magnetron?
Yes.
Yeah.
Thank you very much.
Just popped into my head.
I knew it ended in TRON, but I couldn't remember what it was. It's
via
amalgamated.
the internet, via
Well done.
Google.
Well done, popping into your head.
Yeah, as if.
Yeah. So that's right. They were probably miniaturized as well to the extent that you can. But that spurred on the first generation of sort of smaller computers. We used to use those in the Schmidt telescope when I worked there. We had PDP computers, which were certainly not portable, but they were smaller than those big mainframe machines that we had back in the early 60s. And then the move to personal computers, and of course now to this amalgam of telephone technology and computing, which we all carry in our pockets.
Oh, yeah.
The estimate is that your average mobile phone, in terms of the number of instructions per second that it can carry out, is 120 million times faster than the Apollo computers.
That's just staggering. It's staggering, yeah. And it's happened in 50 years, less than 50, well, probably 40 years in real terms, but. The thought that we are carrying around in our pockets devices that are, that much more superior to something that helped people get to the moon is mind-boggling. It really is. And it's a testament to what was achieved as far as the Apollo missions were concerned, because this was the catalyst for change. This was one of the things that led humanity down that technological path that we all take for granted now in many, many countries.
I think that's true. I think that's a fair comment. And of course, there are other fields as well. Without going into too much detail, for example, fuel cells were perfected for Apollo. These are things that take hydrogen and oxygen and combine them electrolytically to produce power and water. And in fact, I think it was, if I remember rightly, it was an explosion in a fuel cell that led to the Apollo 13 mission abort. I think that's what caused it. I can't remember. I never saw the movie, by the way.
Oh,
Andrew,
right.
I should watch it sometime.
I think you'd enjoy it. You'd probably have a bit of cringe factor because it's such a complicated story. They had to take a lot of shortcuts. So
yeah, I'm sure they would.
A few things are probably not as well detailed, or a bit of creative license went into just we'll just do that, just get that thing done. I thought, if I recall what they said in the movie, it was rotating the oxygen tanks that might have caused the explosion.
Maybe.
I can't remember.
But I don't know.
Yeah.
Don't know. But fuel cells now, they're at a much higher level of sophistication than they were back in the days of Apollo. And they've got a bright future. Certainly our chief scientist, Australia's chief scientist, Alan Finkel, whose office is just along the corridor from me when I'm sitting in Canberra, he is a great champion for hydrogen fuel for cars. And the way you turn that fuel into energy is not by burning it, but by putting it through a fuel cell, so that you get power and water out the other end, hydrogen and oxygen. So he sees a bright future for hydrogen power, and he's a very strong advocate for that.
As a side note, I got a survey the other day from a car company. I bought a car from them 4 years ago, and I sold it not long after, to be honest. But they still survey me about how the car's going, and I keep saying I don't own it. But one of the questions in the survey was, in future, perhaps when you buy your next car, will you buy a fuel, a diesel, a full electric, a hybrid, or a hydrogen-powered vehicle?
There you go. Yeah, that's right. Yeah.
Which aren't available in Australia, as far as I'm
aware.
No,
they're not. No, but that's the correct answer. But yes, they're not available.
Yeah. So there's a lot to sort of look at technologically speaking. Yes, in terms of what.
Indeed, that's right.
Apollo. And
just looking at the big picture stuff, the rocket science itself has changed since Apollo. I mean, as I said, Apollo the Saturn V was the biggest launch vehicle ever produced that's ever left the Earth. 110 meters tall with all the the gubbins for Apollo on top. But we're well on the way to spacecraft or launch vehicles of comparable power, but which will be much cheaper. And you've got to give people like Elon Musk credit for that, for his reusable boosters. That's, you and I have waxed lyrical about this several times. It brings down the cost by probably a factor of 10. So, eventually, what now costs 20,000 kilograms to go into orbit will come down to 2,000 kilograms per launch, something like $2,000 per kilogram. Currently $20,000 per kilogram, but will come down that factor. And in general, I suppose, the amount of use that's now made of space compared with what it was like in the Apollo era, there were a lot of scientific satellites, there were a lot of military satellites, there were a few communication satellites in the Apollo era. But look at where we are now. There are something like 5,000 satellites in orbit around the planet. About 3,000 of them are defunct. So there's something like 2,000 operational ones. A statistic that I noted recently and hadn't realized was that last year, 2018, on average, there was one satellite launch per day.
Wow.
I think it was 380 something for the year, so it was about one per day. But of course, there's all the debris as well. Something like 500,000 bits of space junk up there, larger than a coin. Most of that's tracked, so that you know to move the International Space Station out of the way, one of these bits is going to whiz by. I think, it made me think about this. I suspect that's one of the less welcome legacies of Apollo, is what we've done to our environment in space. We've really cluttered it up.
And, of course, the Deep Space Network.
Yeah, the Deep Space Network. That's right. I was going to highlight that too, because that's something we take for granted in terms of the way the data come back from the robotic space probes. This Deep Space Network of dishes. The three main ones are at Goldstone in the USA. It's in California. The European one's near Madrid. That's a well-established station, goes back to the Apollo era, and of course. What is now Tidbinbilla, but was Honeysuckle Creek, where the first images of Neil Armstrong's moonwalk came through, and Parkes, which took over soon after that. Tidbinbilla now has the function, Tidbinbilla just outside Canberra, of being NASA's Deep Space Network station in Australia, although I think Parkes gets roped in it still from time to time.
Yes, indeed. But so much that came out of the Apollo missions scientifically. So, if you're listening to us via your smart device, that's one of the legacies of Apollo, and something we all love so much these days and cannot live without. You're listening to Space Nuts with Andrew Dunkley and Fred Watson, a special edition looking back at Apollo 11 50 years on.
Okay, we checked all four systems and keying with a go.
Space Nuts.
Finally, Fred, we're going to look at what we call the intangible legacy. Science and technology would be obvious things to discuss out of the Apollo program. But the intangible. Now, one of the things you're about to talk about blows my mind. And I think a lot of people will be quite astonished by it. We might as well start on that very point.
Yes, you mean the idea that perhaps the Apollo missions have averted World War III?
Yes, indeed.
Yeah. Look, at the beginning of the 60s, this is the Khrushchev era in the Soviet Union. Relationships between these two superpowers were not good, and there were a number of very near misses. The Bay of Pigs comes to mind and things of that sort. These were in the very early 60s.
Yep.
They were sort of bristling at one another. In a very ugly way. And actually, I remember, I lived through all that. It was pretty scary from time to time. In fact, I lived during the Apollo era, I lived right next door. I was at university right next door to an RAF base, Royal Air Force base. And they had fighters which were ready at the end of the runway to scramble in case of a marauding Russian bomber coming into British airspace, and they scrambled about once a week.
Gosh.
Because the Soviet Union was probing all the time the defences just to check everything was all right. I used to speak to a lot of the pilots and their support staff, and apparently some of these encounters were quite friendly. The Russian crews would be waving through the windows at the lightning jet fighter pilots and.
Oh, the Lightning! That is a beautiful aircraft. I built a model of it as a kid. Gee, I loved that plane.
Yeah, they were. Anyway, look, it was very much a real threat, and he lived under that shadow particularly during the 60s.
Well, even when I was in high school in the 70s, Fred, we grew up with the same fears. That was the number one concern amongst young people in the 70s was nuclear war.
Nuclear war, that's right. So, in some ways, Apollo might have acted as a safety valve for that. And you and I have spoken about it before. There was a competing Soviet venture. The project was called N1, and the N1 spacecraft, or the launch vehicle, looked a lot like the Saturn V, except it had slightly bulbous first stage because they used spherical fuel tanks rather than cylindrical ones. But the N1, sadly for the Russians, it never succeeded. Probably because it was a bit technically advanced. Whereas the Saturn V, the first stage had 5 gigantic rocket motors doing the business and burning 13 tons of fuel per second, the N1 had 30 first stage rockets, which were a bit more technologically advanced than I think they were the F1 engines, the Rocketdyne F1 engines that were on Saturn V. But the Russian ones, whilst they were more advanced, they never managed to harness them all to work simultaneously because of vibrations probably that were set up in the frame of the spacecraft when you blasted all these 30 engines off at once. So I think there were 4 test launches, none of which succeeded. None of them were occupied by humans, so they were all trials. So that kind of took a little bit of the tension out of the Cold War, and just maybe Apollo actually prevented something really horrible from happening.
Yeah, maybe. There was also the cost factor too, wasn't there? That's
right. Yes. So while Apollo was running. At its height, it was using up 4% of the national budget, the federal budget in the United States. For about the last decade, NASA has been about 0.5%. So that just shows, it was a factor of 8 more than it is now, just to get the project running and to get it going.
Which would have made it hard to finance a war.
Well, it took. I mean, the problem was that in the end, it was a war that actually, to some extent, helped to shut down the Apollo projects because the US got involved in Vietnam.
That's true.
It was once again, and I suppose you could call that a proxy war with the Soviet Union. It was, but it wasn't a world war. It was, not one that was going to have nuclear missiles whizzing all around the place. So just maybe the Apollo did divert some attention from that. But on a more perhaps benign or benevolent note, Apollo changed the way we see ourselves as a species because for the first time we could see the Earth as a planet sitting there and see how fragile the environment is. It was, I remember this so well, Christmas Eve 1968, Apollo 8 was in orbit around the moon. It was one of the trial missions before Apollo 11. Bill Anders, the command module pilot, he took his image of the Earthrise picture. So it's a picture of the Earth rising over the limb of the moon. And people have described that as the most influential environmental photograph ever taken because it just shows what we live on.
Yeah, and it shows the absolute thinness of our atmosphere. How much there really isn't between us and deep space.
That's right. There's 10 kilometres basically. Yeah. By 10 kilometres high, you're above 75% of the atmosphere, which is remarkable.
Which, if you walked in a straight line, would only take you a few hours. The average
that's
person.
Right. Not very far. That's right. Doesn't take you long to drive 10 kilometres.
No. Well, to be honest, when I play 18 holes of golf, I walk 10 kilometres.
Yeah, 7 miles per hour.
Yeah, which is, not far at all.
Not far. And I suppose, Andrew, that led eventually, and some 20 years later, to the the famous pale blue dot image of our own planet, which was engineered by Carl Sagan, who was involved with the Voyager 1 mission. Voyager 1, of course, one of the 5 spacecraft leaving the solar system altogether. It's now, I think it's something like 20 billion kilometers from the sun. But in 1990, St. Valentine's Day, 1990, I love the fact that he chose that. They turned the spacecraft around and pointed it back towards the inner solar system and took an image which shows the pale blue dot of our planet. It's got it's an image that's actually got some streaks on it, which come from the fact that they were relatively close to the sun in the sky, and that's interference from the light of the sun. But nevertheless, a very clear image. If I remember rightly, it's about a tenth of a pixel in size on the Voyager 1 camera of our own planet. And it was, at that time, about 6 billion kilometers away. Sagan was so inspired by that image that he actually wrote a book about it, Pale Blue Dot, which includes words that I think have become, almost biblical in their import. They're very, very well-known words, but I've got a quotation here, but I won't read it all out. I'll just read the beginning. What he says is, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love. And he sort of goes on, and it really brings home that, yes, this pale blue dot is it, as far as we're concerned. Forget about colonizing Mars. Yep. It's our pale blue dot, and we really need to look after it. And to some extent, I think that really, kicked off the what we see today as the environmental movement, which certainly wasn't there back in the in the 50s anyway. It was just starting to get going in the 60s, and I think Bill Anders' Christmas Eve image from Apollo 8 helped, but it was certainly spurred on by Carl Sagan and his pale blue dot. All a part of the legacy of Apollo.
Indeed, Fred, indeed. And I just want to finish off on what I heard about another photograph that Michael Collins took. Now, and it sort of relates to what Carl Sagan's words reflected just then. But apparently, and I did look this up, Michael Collins took a photo, not dissimilar to the Earthrise photo, from the capsule.
Of Apollo 11.
Yes, as he was orbiting the moon. So you've got the moon in the foreground, the Earth in the background, and they say it's, and apparently within the photograph of the moon portion, the 2 astronauts are on the surface at that time.
Yeah.
They say it is the only photograph in human history that shows everyone who existed before and during humanity's existence, except for one person, and that's the guy who took the photo.
Took the photo, yeah.
Michael Collins. So he apparently will go down in history as the only person ever to not be in a photograph.
Of everybody else.
That's mind-blowing in itself. I know it's fairly anecdotal, but I love that story. Story.
It apparently
it's almost as good as Mr. Gorski.
Oh, the Mr. Gorski story, yeah. No, we can't do that
Which
one.
we can't explain, but people will have to look that up for themselves.
Yeah, I think Michael Collins actually had quite a good time on his own in the
I understand it. I heard him in an interview only a few hours ago, in fact, saying just that. I had my music and I had a good time. Coffee. Great. It is a great story, and it's a fabulous story. It's good that 2 of the 3 are still around. I'm sorry that Neil Armstrong didn't make it to the 50th, but he will always be remembered as the first human being to set foot on another world. i.e. not a planet.
Yes.
But yes, but the day will come when someone else will step on another planet. I am certain of that. And
yeah, I hope
that's
you and
probably not far off, really, in the scheme of things.
I hope you and I are talking about it on Space Nuts as well.
I hope so too. Fred, it's been a pleasure. Thank you for doing all that homework and putting all that together. I know you worked very hard on that, and you've got a lot of media commitments surrounding this 50th anniversary. So thank you. It's always a great pleasure, but this one especially, because this takes me right back to one of the great moments in my childhood that has been with me ever since. And I see that as probably an influential part of my life and many people's lives, even if I was just an observer. It's just one of those keystone moments in humanity, I think, and it was just a great privilege to be able to witness it, even on an old black and white television.
Yep, I agree with all of that, and you're absolutely right. That's the way I feel about it too. So it's a pleasure, Andrew. It's great to have the opportunity to have a conversation like this, and we'll get back to Earth next time, perhaps.
Indeed. We'll catch you next time, Fred. Thank you very much. And from me, thanks as always for listening to Space Nuts. No questions this week because obviously we wanted to focus on this particularly special event, but we'll be back to normal next time on Space Nuts. Oh, and good luck, Mr. Gorski.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.